Flipped classroom video for Maths AS Unit 2, Vertical Motion Under Gravity. We're going to consider objects now being thrown vertically, and the only force acting on them would be the force due to gravity. Some time ago, Galileo discovered that a body dropped at any point near the Earth's surface experiences a constant downward acceleration of about 9.8 meters a second squared, provided that the air resistance on the body was negligible. In fact, there is a slight geographical variations in the magnitude of this acceleration close to the surface due to the fact that the Earth is not a perfectly uniform sphere. Moreover, the acceleration due to gravity does decrease with the altitude of the body above the Earth's surface, and the table illustrates this variation. So if we're at 0 kilometers above the Earth's surface, the downward acceleration is 9.8 meters a second squared. Even if we're at 1 kilometer above the surface, it's still 9.8. Even if we're 10 kilometers above, it's very close to a 9.8 meters a second squared. So if an object is moving vertically close to the Earth's surface, and the only appreciable force acting on the body is its weight, in particular the air resistance is negligible, then the altitude of the body above the Earth's surface does not exceed 10 kilometers, then the body will experience a constant downward acceleration of 9.8 meters a second squared, and the motion of the body can be modelled using the constant acceleration equations. So, first example, a ball is thrown vertically upwards with speed of 18 meters a second from the top of a tower of height 15 meters. Find the time for the ball before the ball hits the ground and the speed which the ball hits the ground as well. So two parts to this one. It's nice to draw a diagram first so you know what's going on. So there's the initial position. At the top of the tower is being thrown vertically upwards with a velocity of 18 meters a second. It goes up, it stops, and then it comes back down. And its final position is on the floor, 50 meters per second below the top of the tower. We've got 9.8 acceleration due to gravity pulling down, but it's important that we decide which is our positive direction. Being as it's being thrown up, we're going to take the positive direction to be up. So anything pointing downwards is going to have a negative value. In considering the motion of bodies under gravitational acceleration, it's important to be clear which direction is being considered as the positive direction. It's a good idea to indicate this clearly on your diagram you draw at the beginning of your solution. So part A, what do we know? We know that A is minus 9.8. It's acting down, it's pulling it back down to the Earth. U is 18, the initial velocity going up. X, V we don't need, so we put a cross there. That's one we don't want. T is what we want to find. S is our displacement, is minus 15 because it's below the level 0 that it's being thrown at. So we take where we are throwing it to be 0. So our displacement when it hits the floor again is going to be minus 15. We don't want V involved at all, so we're going to use the equation S is equal to ut plus a half at squared. Putting in values, we've got minus 15 equals 18t plus a half times minus 9.8 times t squared. So we've got minus 4.9t squared. Collecting terms one side because we have a quadratic, we get that expression. Either use the calculator to solve this quadratic or use the formula, and we get that t is equal to 4.373, or that t is minus 0.700. Now the minus would be the time if before we started timing, when the particle would have been on the floor. It's an algebraic equation. But at the moment we don't want the minus, so we're going to cancel that one. So the ball hits the ground after 4.37 seconds. Notice that we do not need to consider the upward and downward motion of the ball separately, since the acceleration of the ball is constant throughout the motion, and the constant acceleration equation can therefore be used for the whole motion. We don't need to do two parts to the motion, up until it stops and then back down to the floor. We can do the whole motion in one go. Now we want the speed with which the ball hits the ground. Now there's two methods of doing this. So first, using what we've got, not what we found out. Not using the t, because it might have been wrong with us. So if we use that equation, v squared is equal to u squared plus 2as, we get, putting values in, 18 squared plus 2 times minus 9.8 times minus 15. That works out to be 618, taking the square root. We've got a plus and minus velocity. Now think what's happening. If it was going up, it would be plus, but being as it's coming down to hit the floor, so it's got a velocity of minus 24.86, but we only need the speed. So the speed is the magnitude of that, which is 24.86 meters per second. Now the second method would be using that t that we found out in part A. So using t is 4.373, when the ball hits the ground, we can use this equation to find v, and we get the negative answer straight away because we are using the positive t, so we get the actual velocity when it hits the ground, so that then the speed is also going to be 24.86 meters per second. So second example, a stone is thrown vertically from the top of a cliff 30 meters high and later hits the sea below with a speed of 27 meters per second. Find the possible initial velocities of the stone and the corresponding times of flight of the stone before it hits the sea. Now it says it's thrown vertically, but it doesn't say it's vertically up or vertically down. That's why it says the possible initial velocities. So we start with the diagram. So we're taking up as positive. So we're considering u to be positive to start. We know the tower is 30 meters tall, so that displacement would be minus 30. It's going to hit the sea now with a speed of 27, so the velocity would be minus 27, and our acceleration due to gravity is minus 9.8. So putting those in, we don't want the t. Later we'll want the t. We want the initial velocity, so we want u. That's what we want to find. So we're going to use the equation that doesn't use t, which is v squared is equal to u squared plus 2as. Putting values in, we've got minus 27 all squared is equal to u squared plus 2 times minus 9.8 times minus 30. Therefore, on the left, we've got 729. On the right, we've got u squared plus 588. So u squared would be 141, and u would be plus or minus 11.87. Therefore, either we throw it up with a velocity of plus 11.87, or we are throwing it down with a velocity of 11.87 giving us the negative velocity for going down. Now, we need the times for each of these for the stone before it hits the sea. Now, we could use a different equation, but if we use this equation, we are not using the u. We are not having to do the equation twice. So we can use s is equal to vt minus a half at squared. U doesn't come into the equation at all. So that gives us minus 30 is minus 2070 minus a half minus 9.8 t squared. We've got a quadratic in t again. So plus minus and a minus is plus 4.9 t squared minus 2070 plus 30. Solving this on your calculator or formula, and we get t is 1.543 or t is 3.967. Therefore, if it's thrown downwards, it would take shorter time to hit the sea, so it would be 1.543. If it's thrown upwards, it would have to go up and then back down, so that 3.967 would be the time if it was thrown upwards. Therefore, if u is plus 11.87, then the time is 3.967. If u is minus 11.87, then t would be 1.543. Therefore, draw a diagram, decide what values you want, and think about what is happening in each example. And that's the end of that video.